So hello and welcome for today's session. So today we're going to talk about the orthogonality of four subspaces. So in the previous tutorial we have talked about the dimension of the four subspaces. So I'm going to quickly revise it because we are going to elaborate or we are going to apply the orthogonality on these subspaces which we had discussed in the last tutorial. So if you look into the dimension of the four subspaces here, we have the four subspaces that we have talked about, that is the row space, column space, null space, and the null space of A transpose, or it is also called as a left null space. So all these subspaces, now if we talk about the row space, it is the row space that is represented as a C of A transpose is a subspace of R power n. It means it is the dimension of R power n, and it's what do you say that we have shown the proof of all these, what is rank of this matrix and what is the basis of this matrix. If you have not referred it, I ask you to refer the previous tutorial to understand it much better. So whereas here the rank of the matrix is equal to the dimension is equal to the rank of the matrix. So the column space is represented as C of A, and it is a subspace of R power m, and here also the dimension is equal to the rank of the matrix. Whereas the null space n of A is a subspace of R power n, and here the dimension is equal to n minus R. And here the null space, the left null space, it is a subspace of R power m, and here its dimension is defined as m minus r. So these are the important things that we have discussed in the previous tutorial. So now we are going to apply the orthogonality, and we'll show what is the relation between the row space and the null space and the column space and the left null space. So this is what very important. So today we are going to talk about the orthogonality of these four subspaces. So the other definition of the orthogonality is nothing but the perpendicular, means these subspaces are perpendicular to each other. So let's hit back to our screen here. So before that, let me enable the other things for you. Okay, so we are in here. So now let's talk about the orthogonality. So the very first condition for the two vectors to be orthogonal is that their product should be equal to, their dot product should be equal to 0. So that let me write here the definition, that the two vectors are orthogonal when their dot product is 0. When the dot product is 0, so it means suppose we have a vector v into, we have one more vector w, that dot product should be equal to 0. Or if we have the v transpose, so that I'll write in dot product with the w should be equal to 0. So I'll write here. So if we have one more vector here which is a transpose of v, even then the v transpose into v should result in the 0. So then we will say that the two vectors are orthogonal or perpendicular to each other. So we can also visualize this with the help of the right angle triangle or the Pythagoras theorem. So we know the Pythagoras theorem that says that that is a square plus b square is equal to c square. So this forms the right angle here. So we can also write this in terms of, say, the so v square here, which is equal to the v plus w square. So the Pythagoras theorem in the form that we can write here. So anyway, we will talk about this more later. So we'll see here. So one of the definition that we're going to look into that is that always we used to write that ax, a into x either is equal to b or equal to 0 for the null space. So it means that So the matrix A multiplies a vector. So A is nothing but a matrix. It might be an any dimension of matrix. It is M cross N matrix. In generally, it is going to multiply. It means a vector. So suppose we have the vector. This is x1. This is x2, and so on up to whatever the values here. So it is should be equal to xn. So then, so A multiplies a matrix multiplies a vector, so it means it is A times x. Okay, so we'll write one diagram here and we'll try to correlate that all the four subspaces. So let me write that quick diagram, so then we will discuss all these things here. So that is, so this is my row space, and this is the null space, and consider that it forms a right angle here, and so we have the column space here, something like this, and then it forms the right angle with this. So this forms the right angle. So this I can write here, this is nothing but the row space of A. This is row space of A. This is row space of A, and this is the null space of A, and this is the column space of A, and this is the null space A transpose. Null space A transpose, that I'll write here. This is null space A transpose, and here it has a dimension of r power n. As I told you before, the row space has the dimension r power m, and the column space has a dimension r power m. And here the dimension of for the row space, which is equal to the rank of the matrix, and here the dimension for the null space, which is equal to n minus r. And here if you see that the dimension for the A transpose is equal to m minus r, so it is m minus r, and here the dimension D is equal to r. So now if you see from these diagrams here, the row space of A is perpendicular to the null space of A, and the column space of A is perpendicular to the null space of A transpose. So that is the relation that we're going to talk about here. It means these are orthogonal to each other. So let's take the first one here, that is the row space is perpendicular to the null space. Here every row of A is perpendicular to the solution, means every row A is perpendicular to the solution, that is Ax is equal to 0, and it forms the 90-degree angle on the left side of this diagram, and this forms the part 2 of the fundamental theorem of the linear algebra, the perpendicularity of subspace, in part 2 of the fundamental theorem of the linear algebra. And if you look into the right side of this diagram, this is the column space is perpendicular to the null space A transpose, where so this we'll use when B is outside the column space. When B is outside the column space, and we cannot solve the solution here when Ax is equal to B. When we cannot solve it, then we'll go for the error function, that is E is equal to B minus A into x. So this is called as the least square method, so least square solution. So then we'll go for this column space and the null space of A transpose. So in terms of dimensionality, the right dimension comes from, so we have the different dimensions for all these. So this is r power n here, this n, uh, the dimensions are different. This is r, this is n minus r here, m minus r here, dimension is r. So now the row space and the null space are orthogonal subspaces inside the R power n. So what is the dimension? What is the subspace here? The subspace and both of these vectors, or both of these row space and the null space are in a subspace inside R power n. So let us look into the deeper definition here. So to look into the deeper definition, let me write here that if you have the two subspaces, if you have two subspaces, that is say capital V and capital W of a vector space, or when we say orthogonal, if every vector, small v, if every vector V in V is perpendicular to every vector in W, every vector in W. So now this is nothing but the orthogonal subspaces. So it means that is V into W. So if we talk about the orthogonal subspaces, then V transpose into W should result in zero vector. So for all this, so this is applicable for all V in V and all small w in W. So to understand this perpendicularity, we can talk about one of the example here. So for example, we have the floor, and which is of extended to infinity, and the two walls are joining. So then this is our floor, and the two walls are joining. The line where it is joining, so this forms the perpendicular of every vector in the floor. So here, so the line where the two wall meets is the subspace W. So this we can call the subspace and W in one dimension, and those subspaces are orthogonal. So every vector up the meeting line is perpendicular to every vector in the floor. So now every vector in this is equal to every vector in the floor. So to better understand this, we will take one example here. So let me save this page. Take the new page here. So let us take an example. Say we have the two vectors, that is we have two vectors, that is -1 and 2. So these are the column vectors, and the one more vector we have, that is 4 and 2. So if we take the dot product of these two vectors here, so that is -1 into 2 into the transpose of this. When we take the dot product of this, that is 4 into 2, that is inverse, when we take the transpose, then what do we get here? Is it right? No, I think I have interchanged this. This is not right. So what I will do is that I'll write this on this side. Let me move this as well. Yes. Now when we write this, what do we get here? That is now this is 4, sorry, this is -4, we'll get +4, so which is equal to 0. So the dot product, when we said, so these are the two vectors, and the dot product will result in the 0. So that is what we have talked about. If we have the two vectors, that is V and W, then V transpose into W. If we have the two vectors V and W, then V transpose into W results in equal to 0. So that is what we have talked about. So this you can consider this is V, and this is a W vector. So here we are represented in the form of V transpose into w, which is equal to 0. So now if you draw these vectors on the two-dimensional plane here, so let me draw it here itself below. So we take the two-dimensional plane here, and if you draw the two vectors here, so the first vector is 4 and 2. So let's take the two plane. So 4 into 2 might be somewhere here. So I get this one vector here. So this is 4 and 2. Then the other vector, that is minus 1 and 2. So minus 1 and 2 might be here. So this is minus 1 and 2. Now if you look into these vectors, now these vectors forms the perpendicularity to each other. So they are perpendicular to each other. So if you do the x minus say y, then we may get a vector which is somewhere here, the 0 vector here at the dot product of it. So now this is what we are talking about, the perpendicular and the orthogonality of the two vectors. The two vectors are orthogonal to each other. So likewise, when we talked about the previous example, we have the floor and the two walls are joining. So that line of the join, so that forms the subspace in our subspace, and that forms the orthogonal to the vector, perpendicular to every vector in the floor. So that's it. So now here the main important point is that the 0 is the only point where the null space meets the row space. So when we look at the previous diagram that we had written, so where the row space and the null space are meeting, so let me come here and let me write the same the previous diagram. So the previous diagram we had written yeah, so something like this. So this is our row space. I'll just write it as R, and we have the column space here. So I'll just write that as n of AT. So this I'll write this as a representation C of A transpose, because that is how we'll represent this, and n of A is the null space. So now if you see that where these points are meeting, so this is at the point of 0. So 0 is the only point where the null space and the row space are meeting. So more than that, the null space and the row space forms an angle of 90 degrees. So this forms the angle of 90 degrees, and they're in the subspace of R power n. So this happens because their AX, the null space, is nothing but the AX is equal to 0. So here every vector x in the null space is perpendicular to every row of A, because AX is equal to 0. So the definition goes like this. So if you write that in terms of definition, so then every vector x in the null space is perpendicular to every row of A, because AX is equal to 0. AX is equal to 0, the null space n of A, and the null space n of A and row space C of A transpose, so that I'll write later, C of A transpose, or orthogonal subspaces of R power n, so that I'll write here. So just you have to understand that the null space and the row space are orthogonal to each other, and they are in the subspace R power n. So just for illustration, we will take an example here. So for example, we have AX, which is equal to, so if the matrix A is some m cross n matrix, and we have certain rows, so for example that is row 1, and likewise up to we have row m, So we have row m, and then we have a vector of unknowns, that is x here. So that is x, and that should be equal to 0 zeros, right? So it means there is nothing but here the row 1 is and the dot product with x is 0, then the row 2 into the next value of x is again 0. So now the row times the x is equal to 0. So that is what it means. So every row has the 0 product with x. So if you talk about the null space and row space another way, yeah, let's take one more example here to understand. So let me save this page here. So we'll take a row of A and a row of A are perpendicular to X. So we define here our row matrix as 1, 3, 4, and the second row is 5, 2, 7, and our X, it is the vector is 1, it is 1, 1, minus 1. So this should be equal to what? So this should be equal to 0. So let's see whether this is equal to 0 or not. So definitely when you do it, so it is 1 plus 3 minus 4, which is equal to 0, and here that is 5 plus 2 minus 7, it is equal to 0. So now what is the dimension that we are living in? So it depends. So for the column space, so for the so this is results in the same example. If you look into the column space, so where it is in R square, so then the null space of A transpose is also a 0 vector. If we take the A transpose and we see the perpendicularity or orthogonality with respect to the column space, so this will also result in a 0. So let me write that definition also here. So every vector y in the null space of A transpose, that I'll write later, is perpendicular to every column of A. It means every vector y in null space of A transpose is perpendicular to every column of A. Then the left null space n of A transpose and the column space C of A are orthogonal in R power m. Is orthogonal in R power m. So this is A transpose, and this is R power m. So here if you look into the definition once again, so every vector, this is every vector y in the null space of A transpose perpendicular to every column of A. So it means the null spaces transpose are perpendicular to each other, and the left null space, that is null space of A transpose, and the column space of A are orthogonal in R power m. So then that can be represented in a symbolic way, that is written as that is C of A is perpendicular to the null space of A transpose. So even the general form of writing, so we can represent that in a very general way, that A transpose into Y, which is equal to, suppose we have the column, so the column 1 transpose, then we have column 2 transpose, and all represent multiplied with y, so that should also result in zeros. So that is what it means. So now we will look into the orthogonal components here. So let's look into the orthogonal components here. So not components, the orthogonal complements, sorry. Let me write the heading here. So the definition of orthogonal complement goes like this. So the orthogonal complement of subspace V contains every vector that is perpendicular to V. So this orthogonal subspace is denoted as a V perpendicular. So let me write the definition here. The orthogonal complement of a subspace V contains every vector that is perpendicular to V. This orthogonal subspace is denoted by, so that I'll write here, that is V perpendicular, like this, V prop. So by the definition, the null space is orthogonal complement of row space. So the null space is orthogonal complement of row space. So every x that is perpendicular to rows satisfies ax is equal to 0. So if you talk about the row space, the row space which grows and then it breaks a rule. So for example, now what is the dimension of the dimension of the row space? The dimension of the row space is I equal to r. So this is the dimension of the row space, and whereas the dimension of the null space is n minus r. So but if V is orthogonal to null space, it must be in the row space. So then the dimension is concluded to be the row space will grow, then it breaks the law that n plus n minus r, we get the dimension as n. So this is, we call it as the full dimension. So likewise for the null space and the left null space and the column space, then it is. So that is why in the, if you look at the previous diagram that we had written, there we had written that the row space and the the row space and the column space are in the subspace r power n. So how that r power n comes into effect is that, so it violates the law, and then the full dimension it comes into effect. So full dimension for the column space, for the row space and the null space is r power n, whereas on the other side we had, that is on the right side, when we talked about the column space and the when we talked about, say, column space, that is a C of A, and we talked about the null space of A transpose, so their dimensions were D is equal to R, and this D is equal to M minus R. So then here R get cancelled, so again the full dimension we will get here as R power M. So that is what we had written. So let me write in terms of the statements. So this forms the part 2 of the fundamental theory of the linear algebra. So this forms the part 2 of fundamentals linear algebra. So the 2 points which we just discussed, so that goes like this. So that is n of a, is orthogonal complement of row space C of A transpose in that is R power n, so that I will write later, and whereas the n of A transpose is orthogonal complement of column space C of A in R power m. So let me complete. So this is C of A transpose into R power n, and this is in R power m. So now we have seen the part 1 and part 2. So part 1 gives the dimension of the subspaces and part 2 gives the 90-degree angle between them. So the point of complement is that, so every x, so what we can do is that we can split the x into row space components and the null space components. So the x can be written as, so x is equal to the row space components, that is xr, plus we can write this as equal to xn. So this can be written as xr plus xn. So row space components and null space components. Then we multiply with the matrix A. Then the null space components goes to, then the null space components, we can write this is equal to A into, generally rather than writing this entire x, I can just write this as A into xn, which is equal to 0, and the row space components goes to, so A into xr, which is equal to A into x. So then if we relate this, so then we enter into the new phase which relates that. So if you look into this definition here, A into xn means the matrix times, or A times the null space of x, that is xn, is equal to, results in the 0 point and the r power m, and whereas A into xr is equal to A into x in the column space. So that is what we are going to write this relation. So I'll copy this so that we can use it later in the new page. So let's write the same diagram which we had written before. So that is we have the column space here, sorry, we have the row space, so that's, we can represent this as C of A transpose, which is perpendicular to the null space. So this is n of A, and these two are perpendicular. This is in a subspace of R power n, and this is a dimension of R, this is a dimension of n minus R. So now if we look into the column space here, so this forms the, this is C of A, and this is n of A transpose. So now we have the point here, so this we can call this as xr, and we have the xn here in the null space xn. So if we add both of these, we'll get x. So this is nothing but x is equal to xr plus xn, and these points, so now here this will result in the point B. These two will result in a point B in the column space when we multiply, or the A, when we perform A into XR, which is equal to B, and when we do A into XN, will result in 0. So this will result in 0 when we perform A into XN. So these are the important points here. So every vector B in the column space comes from so this is another thing, from one and only one vector, that is a row space. So this is it. We have shown the relation that X can be split into the row space components and the null space components, and when we take the dot product of the A times the matrix A times the XR, which is equal to B, so that will result in the column space a point B, and A times the XN, then it is equal to 0, so that will result in the 0 vector in the space of R power M. So let's take one example here, and that forms the subspace. Okay, we'll go for the next topic. So this anyway it's already discussed. Yeah. So the same thing which is written with the help of example here. So let's take an example here. So if you have a matrix A that is 1, 2, 3 and 6, then if you have the X that is nothing but that is equal to 4 and 3, so we can split this into the row space components and the null space components as that is XR plus XN, which should be equal to, if I split this, then I can write this as equal to 2 and 4 plus, we can write this as 2 and minus 1. So we'll get the same thing. So here the vector 2 and 4, 2 comma 4 is in the row space. The orthogonal vector to the orthogonal vector 2 minus 1 is in the null space. So this is what we can say this, and next we will talk about the projections. So when we talk about the projections, the same, these vectors we can represent. Now when we have written that is V transpose into W, if we write in terms of this, which is into, if these are perpendicular to each other, then that is into multiplied with the cos theta, so that will result into 0, because cos 0 is, cos theta, when we multiply, so this will give us the perpendicular when the cos 90, when these are perpendicular to each other, so this will result in the cos 90. So cos 90 degree will result in, multiplied with all these things, which will give us that is as 0. So now if we look into these two examples here, so that is 2 and 4, so whether their forms are perpendicular or not, let's see. So if you have the two planes here, so if I take this first one, that is xn and xr, so xr will be somewhere here, that is 2 and 4. So 2 and 4 will come somewhere here, so this might be the vector 2, 4, and then if I take this 2 and minus 1, so I'll get something like this. Now this doesn't form the perpendicular, this goes in the different phase. Anyway, so that's it for today's session. So today we have talked about the orthogonality. So the points that you have to remember is that in terms of orthogonality, the row space is perpendicular to the null space, and the column space is perpendicular to the null space of A transpose. And here the points that is A into XR is equal to B, so that will transform, or that will result in the B in the column space, and the A into xn equal to 0 that will result in the 0 vector in the R power m subspace. So thank you.